So, hi friends, today we are going to talk about chemical equilibrium, what is equilibrium in general, and what does it mean, how do we solve different kind of problems using the concept of chemical equilibrium. Basically, chemical equilibrium helps you to find out how far a reaction will go and how much of the reactant would be left after the reaction is complete and how much of the product will be formed. So predicting things like that, you can do this with the help of chemical equilibrium. Okay, so we all have seen physical balance, which is basically uh, you have two parts here, and you can put things on this side or this side, and depending on which side is heavy, this will go up or down, right? So chemical equilibrium will use a similar concept. So equilibrium means the stage where, let's say this is a seesaw and there are two balls here and there's a just one ball here. So what will eventually happen is this side being heavier, the balance will tilt in the favor of heavier side. So it will be something like this, where you have heavier thing going down. Similarly, if there was a higher weight on this side, then it will tilt on this side. Now what happens in chemical equilibrium is, at any point of time, there are two kinds of reaction that are happening: a forward reaction and a backward reaction. Now this is applicable only for reversible reaction. That means reaction which can go in both the directions. I am talking only about reversible directions. So chemical equilibrium, when we talk only in terms of reversible reactions, reactions which can be reversed. So at any point of time in a chemical reversible reaction, there are two reactions that are happening. One is the forward reaction and the other a backward reaction. For example, let's say A plus B. So reversible reaction is represented by an arrow like this. So you have a half arrow representing forward reaction and half arrow representing backward reaction. So let's say A plus B gives C plus D. Then molecules of A plus B are combining to give C plus D. That's your forward reaction. And molecules of C and D combine to give you A and B. That's a backward reaction, right? Then there's something called as law of mass action, which states that the rate of a reaction is proportional to the molar concentration of the reactants raised to their stoichiometric power. Okay. So what is stoichiometric power? So whenever you write a chemical reaction, you would balance it and then you would end up writing something like this, some constant like this. For example, let's say this is my reaction, H2 plus O2 gives H2O. So once I balance it, I get something like this. 2H2 plus O2 gives me 2H2O. So here this 2, here 1 and here 2. These are called the stoichiometric coefficients. So law of mass action states that the rate of the reaction is proportional to the molar concentration of the reactants or of the reactants raised to their stoichiometric power. So for a forward reaction, right, my reactants are A and B. So molar concentration, when we represent it like this. So when we say like this, that means the reactant in the square bracket, it means that we are talking about molar concentration. So in this case, for the forward reaction, A and B are the reactants. So A and B. So this is proportional to, rate is proportional to A and B raised to their stoichiometric power, which is A, small a and small b. Right? So, if you remove the proportionality sign, the rate would be equal to some constant, which is a constant for the forward reaction, A raised to the power A, B raised to the power small b, where small a and small b are the stoichiometric coefficients and capital A and capital B are your reactants. Similarly, we can talk about the backward reactions also. So this is for the forward reaction, and for the backward reaction it would be proportional to C and D, their molar concentration raised to their stoichiometric powers. And if we have to remove the proportionality sign, we'll say RB is equal to KB, where KB is the proportionality constant for the backward reaction. Molar concentration of C, which is the reactant in this case for my backward reaction. These two are the reactants and these two are the product. So molar concentration of reactants, which is C and D, raised to their stoichiometric coefficients, which is small c and small d. So this would be my backward reaction, rate for the backward reaction. Now equilibrium, we'll say that it is an equilibrium if rate of forward reaction is equal to rate of backward reaction. That means the speed at which the products are getting formed, at the same speed the product is getting disintegrated into your reactants again. For example, let's say that there's a certain temperature and ice and water are at equilibrium. What does that mean is the amount of ice that is getting changed to water is same as the amount of water that is getting converted back to ice. This is one of the example here. No chemical reaction is happening. It's more like melting and melting of ice and then condensation of ice of water back to ice. Let's look at another example. Something like say this. Say PCl5 disintegrates into PCl3 and Cl2. Right? So this is my reaction. Phosphorus pentachloride reacts with PCl3, phosphorus trichloride. Gives phosphorus trichloride and chlorine. So phosphorus pentachloride gives phosphorus trichloride and chlorine. So this is a reversible reaction. So forward reaction would mean phosphorus pentachloride disintegrating to give you phosphorus trichloride and chlorine. Backward reaction here would mean chlorine and the phosphorus trichloride combining back to give you phosphorus pentachloride. Right? So at a time when the rate at which PCl5 is getting disintegrated to form these two is same as the rate at which these two are combining to give this back, is called the equilibrium. So after that, no further reactant, there would be no change in the amount of reactant or the product. Both will be in equilibrium. That means if let's say at the equilibrium you have 3 grams of this and 2 grams of this and 1 gram of this, then their masses wouldn't change. Or I should say rather the concentrations wouldn't change. It can change only if there's an external factor added. That is, if you add more of this, or you remove some of this, or you add more of this, or you change the temperature, or you change the pressure, or you change the volume of the container in which the reaction is happening. Only in those cases the equilibrium will shift. Otherwise, there wouldn't be any change in the equilibrium. Once the equilibrium is achieved, it will stay there. Unless you change something. Some environment factor, maybe temperature, pressure, volume, or you add some reactant or product. Right? So that is chemical equilibrium. So how does it help? So with help of chemical equilibrium, we'll try to figure out some equation here that will be of our help. Okay. So I'll just remove the lines which are not necessary. So this is my reaction. Let this be there. This is the proportionality equation. I'll remove this. This is again the proportionality equation. Let me remove this also. So now we have a rate of forward reaction and rate of backward reaction. Equilibrium will be achieved when your rate of forward reaction is equal to rate of backward reaction. That means this term on the right hand side is equal to this term on the left hand side. Okay. So if I equate it, I can write it as Kf A to the power of small a B to the power of small b is equal to Kb C to the power of small c D to the power of small d. So for any reaction, we define equilibrium constant as the ratio of Kf by Kb. That is equilibrium constant of the forward reaction divided by the constant for the backward reaction. Once you divide these two, find the ratio of these two, you get equilibrium constant for a reaction. And at that temperature and at that pressure, the equilibrium constant is going to remain same. It doesn't matter what you use. Okay, so let's find the ratio of these two. So if I divide Kf by Kb, so this is called equilibrium constant of the reaction, also known as Kc, and this will be given by Kf by Kb. So Kb comes on the left hand side, and we'll take the A and B term to the right hand side. So you will get C raised to the power of its stoichiometric constant, B raised to its stoichiometric constant, and A raised to stoichiometric constant, B raised to its stoichiometric constant. Right? So this is called the equilibrium constant of a reaction. Okay. Now what does this mean? What does this gives us? So it tells me that for this reaction, this is my equilibrium constant, and if the equilibrium constant is very high, it is more than 1. So that would mean that this product, the product of the numerator, or this overall product of the numerator is much higher than, if it is much greater than 1, than the product of the reactants. That means if Kc is greater than 1, that means reaction, the forward reaction is going to be a lot, because then lot of the products would be formed, then only this would be higher, right? And then that implies this is higher. So if you seeing that Kc is higher, you can imply that the forward reaction is going to a great extent. That means lot of reactants is getting converted into product. Lot of reaction is happening. So it's not necessary that everything. I mean, if you have 100 grams of it, all 100 gram of PCl5 will get converted to PCl3 and Cl2. Only a certain portion of it will get converted. So if your Kc is high, that means you can say that a larger portion of the PCl5 will get converted to PCl3 and Cl2. Similarly, if this is high, that means Kc is less than 1, much less than 1. That would mean the overall concentration of this is higher, right? So then you can say that the reaction is not going to its completion. It will stop somewhere in the starting stages only. It will just a little bit of association or dissociation or the reaction will happen and it will stop, right? So that comes from the fact that Kc is less than 1. So if your Kc is less than 1, that means the backward reaction is preferred. If Kc is greater than 1, that means forward reaction is preferred. Okay? Right. So what happens if we reverse the reaction? What happens to the equilibrium constant? So if you reverse the reaction and write, let's say I write my reaction instead of PCl5 equal to PCl3 plus Cl2, I write it as PCl3 plus Cl2 gives me PCl5. So what happens to equilibrium in that case? So if you reverse the reaction, here in equation 1, your equilibrium constant was given by equilibrium constant of PCl3. Its stoichiometric coefficient is 1, so it will be raised to just power 1. Cl2, again the stoichiometric coefficient is 1, divided by concentration of PCl5. This is for the reaction number 1, right? K1. Similarly, if we have to find K2, Let me rub the things on top. Okay. So if we have, so if you can come here, write it here for this reaction, which is reaction number 2, then K2 would be given by applying the same logic, products raised to the stoichiometric coefficient divided by reactants raised to the stoichiometric coefficient. So here the product is case PCl5. So PCl5 divided by PCl3 and PCl2, right? Now if you see this K1 and K2, which is for this reaction and this reaction, it is opposite of each other, right? Reciprocal of each other. So that means if you reverse the reaction, equilibrium constant gets reversed, right? So for a reversed reaction, your new K would be 1 by K of the old K, right? So if this is for a given reaction, then if you reverse the reaction, the equilibrium constant would be reciprocal of it. Correct? So what happens if we multiply with something? Well, let's say we multiply a reaction by 2 or multiply by half. For example, in certain reactions, let's take an example of water being formed from hydrogen and oxygen. Okay. So you have your reaction as H2 plus O2 gives H2O. Okay. If I have to balance this reaction, I'll have to write 2H2 here and 2H2O here. Now hydrogen is 4, here also it is 4, oxygen is 2, oxygen is 2, it's a balanced reaction. So equilibrium constant for this reaction would be H2O's concentration raised to power 2 by concentration of H2 raised to square and concentration of O2, right? Now if I reverse the reaction and write, that is 2H2O or reverse we have done. So let's say we don't multiply by 2 and balance it. So how do we write it? H2 plus O2 is half O2 will give you H2O, right? So now the new equilibrium constant for this reaction would be concentration of H2O by concentration of H2 and concentration of O2 raised to the power 1 by 2. Correct? Now if you compare these two reactions, square of this is equal to this. That means when we have multiplied the reaction by half, the equilibrium constant gets to root of the initial value. So if this is K and this is K dash, and because this reaction is multiplied by half, this gets K dash would be K power half. You can easily see it, you can square this. So it will be H2O2, H2O2, H2 square, O2 from root it will become O2. So if you square this, you get this. Or if you take a root of this, you get this. Why did the equilibrium constant change to root of the initial one? Because we multiplied the equation by half. So if you multiply the equation by 2, it will become square of this value. So if I write it as 4H2 plus 2O2 gives me 4H2O. So everything I have multiplied by 2, this will become 4, this will become 4 and this will become 2, right? So it has become square of the initial value that we had, right? So if you multiply or divide by any number, then the equilibrium constant gets raised by that number. So if you have multiplied by 2, it gets squared. If you multiply by half, it gets square root of it. Now let's look at one more thing, what we call it as the ice equation or ice box. So ice box means I, C, E. Ice means initial. What is the change? And what is the equilibrium? Okay, so let's say there's a reaction that happens, and some part of the reactants get converted to product, right? So, and then finally you will have some amount of reactant which is left over and some amount of product which is newly formed, right? So you have to write the status of each of the reactant and product at each of the three stages, okay? Or these are your stages, initial, and this is equilibrium or the final, and this is the change that is going to happen. So let's take our old example, which is PCl3 plus Cl2 gives me PCl5. Okay, let's say initially the concentration of each one of them is 1 and the product was 0. So initially only PCl3 and Cl2 was there. There was no PCl5. So reaction happens. Now, as per the stoichiometry, we can clearly say that 1 mole of PCl3 is going to use 1 mole of Cl2 to give 1 mole of PCl5. So if 0.1 mole of PCl3 reacts, it will need 0.1 mole of Cl2 and it will give 0.1 mole of PCl5. Taking it further, I can say that if X moles of PCl3 reacts, it will take X mole of Cl2 to give me X mole of PCl5, because that's how the stoichiometry works here. So the change here would be minus X. Let's say X moles of PCl3 reacts. So change here would be minus X because it is being used up. Cl2 also it will be minus X, and for this it will be X because X mole of PCl5 would be formed. So at the equilibrium, the amount of PCl3 and Cl2 left would be 1 minus X, and the amount of PCl5 that is there would be X. Let's take a more complicated example, or rather something which has basically a different stoichiometric constant. So this is a balanced chemical reaction for formation of water. Let me remove this. Okay. Now, again I am taking 1 mole each of H2 and O2, and so that's my initial thing. I want to figure out what is the change and what is the equilibrium state. Now, if you see the reaction, 1 mole of oxygen needs 2 moles of hydrogen to give you 2 moles of water. That's the reaction. That's the stoichiometry that it says. Okay. So, for every X mole of oxygen used, you will need 2X moles of hydrogen, and that will give you 2X moles of water. Right. That's how the stoichiometry works. So, what I'm saying is, amount of oxygen used is, say, X. So, I'll represent it by minus X. Amount of hydrogen used up would be double of it because the stoichiometric coefficient 2 here. So, the amount of hydrogen used would be double of what oxygen used. So, it will be minus 2x. And the amount of water formed would be 2x. Right. So, at equilibrium, once equilibrium is reached, the amount of hydrogen left would be 1 minus 2x. Oxygen would be 1 minus X, and water formed would be 2X, right? So this is my overall equilibrium condition. If you can write this, then half of the problem is solved, because now if you have to write the equilibrium constant for this reaction, it will just be 2X square. Why 2X square? Because product concentration, which is 2x, raised to its stoichiometric coefficient, which is 2, so 2x square divided by 1 minus 2x, again square because hydrogen has a stoichiometric coefficient of 2, and multiplied by 1 minus x. Right? So it becomes 2x whole square by 1 minus 2x whole square into 1 minus x. That's the equilibrium constant. So if we can write this expression, I can easily write this. And so how will the question come? In the question you might be given this value, which is k, and you will have to find the value of x. Or you would be given x and you would have to find the value of k. That's how the questions, they'll just play around with this equation only in most of the cases. So either you will be given this and you'll have to form that, or you will be given that and you'll have to form this. Right? So that's how it works. Let's look at a question. Let's say this is my reaction, SO2 plus NO2 gives me SO3 plus NO. This is the reaction for which I have to figure out few things. Let's say the initial concentration of each of these gases is 1 liter, right? And the equilibrium constant for this reaction is 16. So Kc is given as 16, which is the equilibrium constant, and initial concentration of everything is say 1. Okay, so you have to find at the end what will be the final concentration of or final volume of each of them, right? So we have written the initial part. Let's write the change part. So let's say x moles of this reacts. It will need x moles of this, and it will give you x moles of this and x moles of that. So the change would be minus x plus x plus x. So at equilibrium, it will be 1 minus x, 1 minus x, 1 plus x, and 1 plus x. Okay, so using this, I can write the equilibrium constant would be equal to product, which is SO3, raised to stoichiometric power, which is 1, into the other one, which is again 1 plus x, and again raised to the power 1, divided by the reactants, which is 1 minus x, 1 minus x, right? So you have Kc given by this expression. Now the value of Kc is given is 16. So 16 equal to 1 plus x whole square by 1 minus x whole square, right? 1 plus x into 1 plus x would be 1 plus x whole square, and 1 minus x into 1 minus x would be 1 minus x whole square. So you get 16 equal to 1 plus x whole square by 1 minus x whole square. Once you take a root of it, you get 1 plus x by 1 minus x is equal to 4, right? I've just reversed the equation and written it, right? So root of it, 1 plus of x square root would be 1 plus x, 1 minus x whole square root would be 1 minus x, and 16th root would be 4. Now what I can do is do a cross multiplication. Okay, let me just rub this. So once I cross multiply, I get 4 minus 4x. This comes this side. So 4 into 1 minus x is 4 minus 4x is equal to 1 plus x. 1 goes that side, 4x comes this side. I get 5x is equal to 3. So you get 3 equal to 5x. So I have written it 5x equal to 3. And finally you get x equal to 3 by 5. That means 3 by 5 mole of SO2 will be used up. 3 by 5 mole of NO2 will be used up. Sorry, liter. We are talking in terms of liter. So 3 by 5 liters of SO2 will be used up. 3 by 5 liter of NO2 would be used up. And what will be formed is 3 by 5 liters of this and 3 by 5 liters of this. So final concentration, as we figured out, was this. So we started off with 1. So we'll be left with 2 by 5 liters of SO2 and NO2 each, and 3 by 5 plus 1, which is 8 by 5 for SO3 and NO, right? So 2 by 5 and 8 by 5. That's how equilibrium works. So you were just given the equilibrium constant, you were given the initial set of concentration of each of the reactants and products, and you were able to predict how much of it would be left in the equilibrium, right? So these all kind of questions we can do using equilibrium. I'll do a few more questions, but before that, let me talk about one of the principles which governs the chemical equilibrium called Le-Chatelier's principle. Okay, so Le-Chatelier's principle. Actually, this principle is based on very common sense. It just says that whenever in a chemical reaction you bring some changes, right? You bring some changes, then the reaction will react in a way so as to negate the effect of those changes. That is very common sense, right? You get hit. If somebody is trying to hit you, you will try to go backwards so that you don't get hit, right? So that's what happens in chemical reaction. How we are going to see 4-5 factors that can affect the reaction, and we'll see how it will affect the reaction. Okay, so the things that can affect a reaction are I mean, even if you think, you can think about those things. First is adding or removing reactants or products. Okay, so let's say I have the same reaction. Let's look at the same reaction: PCl5 plus Cl2, PSL5 giving PCl3 and Cl2. So if you keep adding PCl5, keep adding more reactant, obviously the more of PCl3 and Cl2 will be formed. So let's say you had certain amount of PCl5 initially, and then equilibrium reached, and you had PCl3 and Cl2. You added more of the reactant, that is more of PCl5. So obviously more of PCl5 will start converting into PCl3 and Cl2. So your forward reaction then increases. So how will the reaction shift? Okay, so the reaction will happen so as to use up all those PCl5. Whatever is there, let's use up that, because then only reaction will stop. So ultimate aim of any reaction would be to reach equilibrium. How we can reach equilibrium faster? So to reach equilibrium, they would basically want to get the reaction quotient, which is basically similar to equilibrium quotient. So reaction quotient is the same formula that we use for equilibrium constant for given thing. For example, if this is my reaction, then at any stage of the reaction, whatever is this value, that's called reaction quotient. Right? So this is your same as equilibrium constant. It's just that at equilibrium constant you figure out the concentration at equilibrium. At reaction quotient, the reaction quotient gives you the value of this term at any stage of the reaction. So maybe you started with 1 liter or 1 mole of each of them at the start, and let's say in the previous question the equilibrium was reached when 3 by 5 mole of the reactants were used. So at any other stage, for example when it was half mole, not 2 by 5. 2 by 5 is when the equilibrium is reached, because 3 by 5 gets used up. So at half mole, half liter, whatever is the value of this expression, that's your reaction quotient, right? And if it is less than equilibrium constant, that means there is more to left for the forward reaction. So if R is less than the equilibrium constant, that means more of the forward reaction will happen. If R is greater than the equilibrium constant, that means reverse reaction will happen, correct? Because ultimately it has to reach the equilibrium constant value. So if it has not reached, it will shift in a direction so as to reach that point. Similarly, taking that into consideration, if let's say this equation has reached equilibrium, right? It is in equilibrium state, let's say. Okay, this is equilibrium. Now I add more of the reactants. So that means I am adding more of this denominator, right? So if this increases, the value of this, the overall reaction quotient decreases. So it will be less than the equilibrium constant. And that is why more forward reaction will happen. Similarly, if you add more of products, right? So I keep adding PCl3 and Cl2 into the reaction. So that means this will keep increasing. So overall this will keep increasing. That means that it is more than the equilibrium constant. It has become more than the equilibrium constant. The reaction will shift or tend to shift to the backward reaction. That means backward reaction would be preferred. That means more of PCl3 and Cl2 will combine to form PCl5. Right? Similarly, if we remove reactants, that means reducing this. So overall this will increase. That means it will tend to reach to equilibrium constant easier or faster. Then that would mean the forward reaction slows down, right? Because it is already able to achieve the required equilibrium value without undergoing more reactants getting converted to product. So your favorite forward reaction is reduced. So equilibrium shifts to the left, right? That means if 3/5 was getting consumed earlier, now if you remove some of PCl3 and Cl2, then less than 3/5 would be consumed. So equilibrium shifts to the left side. Okay. Similarly, if you remove product, overall this will reduce. That would mean that it is difficult for you. I mean, it is the reaction quotient is less than the equilibrium constant. That would mean more of backward reaction. It would need more of it. Remove it, that means I'll need more of it. I want to reach this value, I'll need more of it. To have more of this, I need to have more forward reaction. That means equilibrium will shift to the right. Right? So very simple. Reactants you add, equilibrium shifts to the right. Reactants you remove, equilibrium shifts to the left. Right? Products you add, equilibrium shifts to the left. Products you remove, equilibrium shifts to the right. When I say left and right, it means that left means less of forward reaction, backward reaction would be more. Right means more of forward reaction, backward reaction would be less. That again means that more of the, when I say more of forward reaction, that means more of the reactants will get converted to product. When I say backward reaction is increasing, that would mean more of product is getting converted to reactants. So that's what Le-Chatelier principle is or explains about adding or removing reactants or products. Now, let's look at other things. How does other factors influence a reaction? So, let's talk about temperature. So, how does the temperature affect a reaction? So, let's say the reaction is endothermic. Endothermic means when the reaction happens, the heat is absorbed. That means you need to give heat to a reaction for the reaction to happen. In that case, let's say it's an endothermic reaction and the reactants need heat for forward reaction to go through. And you increase the temperature of the system, overall system where the reaction is happening. In that case, the system needs heat and you are giving it more heat. System says, okay, fine, I'm happy with it. I'll do more of forward reactions. But if you reduce the temperature, the reaction will say, the forward reaction will say rather, or the reactants would say, boss, I needed more heat, you're reducing the heat, I think I am not going to give my 100%. I'm not going to react as I was reacting before because you have reduced my temperature, so the forward reaction would be reduced. That means equilibrium will shift to the left. For endothermic reaction, you prefer higher temperature. Better the temperature, more is the reaction. So equilibrium will shift towards right. Lesser the temperature, lesser the forward reaction, equilibrium will shift towards left. Next is exothermic reaction. So more temperature is preferred for endothermic. For exothermic means heat is released. So when the reaction happens, heat is generated, it is released, right? So that means that the system prefers to the reaction to happen at a lower temperature, because then only heat will be released very easily, right? If it is already at a high temperature and then it has to release heat, it will be a little difficult, right? Because the temperature, overall the temperature has to rise. Now rising from a higher level would be difficult. So exothermic reactions usually prefer, or it prefers, lower temperature. So if you increase the temperature of the system, obviously it will say, boss, I wanted to release heat, you're giving me more heat, I am not going to do more of reaction. So forward reaction would be reduced. But if you reduce the temperature, yeah, I'm happy, this is what I prefer. So if you reduce the temperature, forward reaction would be more, and the equilibrium will shift towards right. Right? Okay, so for exothermic, lesser temperature is preferred. For endothermic, more temperature is preferred. For exothermic, you should reduce the temperature. Okay, so I'm not saying that at this temperature the reaction will happen, at this temperature reaction will happen, will not happen. I'm just saying, if for a reaction you increase the system, and if it's an endothermic reaction and you increase the temperature, the reaction will happen more. It will be preferred. But it will, for the exothermic, it will be ulta. That means it will not be preferred. More of backward reaction will happen. That means less of the reactants would react and finally give you the product. Right? So that means equilibrium is shifting to the left. Right? So this is about temperature changes. Now let's talk about how pressure affects the. Okay, number 3 is pressure. Okay, so let's say, let's take the previous example itself, or we'll have to take this example. Right, so this is my balanced equation. Let's say everything is in gaseous state. Everything, even the water that gets formed, is in gaseous state. Okay, so assume that the reaction is happening in a fixed container which has a fixed volume, right? So if all are in gases, right, the total pressure would be the sum of the partial pressure of each of them. That is your Dartle's law of partial pressure. And how do you find that pressure? PV equal to nRT, V is fixed. So depending on the number of moles, pressure would be proportional to number of moles. So if V, R and T are same for all of them, then it will just be, the pressure of hydrogen would be twice that of oxygen, because the number of moles, assuming, is more here. Let's say you have 2 moles of it. Okay, so I'm just explaining in terms of stoichiometric constant how pressure changes. Okay, so now in the closed system, let's say equilibrium is reached. Okay, and I increase the pressure of the system. That means somehow I increase the pressure of the system. So that would mean that it has to negate that effect. How does it negate that effect? So if pressure is increased, that means it has less. As per Boyle's law, the volume should reduce, but the volume of the container is fixed, right? So how do I play around with it? So it would say, let me do one thing. Let me go to a side where there is less number of molecules getting formed, because less number of molecules getting formed means I'll have more space per molecule, right? So I would, then in that way I would reduce the pressure, right? So basically I will negate the effect of addition, increase of pressure. Okay, so it will prefer a direction in which there are lesser number of molecules, right? Increase in pressure prefers a direction which there's lesser number of molecules because you have lesser volume available, right? So where, now the question is where is there a lesser number of molecules? Now in this case, for the pressure case, we will only consider gaseous molecules, right? So how does number of molecules affect or on what factor number of molecules depends? It depends on the moles of the substance because number of molecules is directly proportional to mole. 1 mole is Avogadro number of molecules, right? So less moles means less molecules. Now in this side, if you see, there are the stoichiometric coefficient is 2 and here it is 1. Total is 3. Here it is 2. So that means if forward reaction happens, from 3 molecules you will get 2 molecules. That means overall there is a reduction in molecule count. So you increase the pressure, you will say, boss, let's do forward reaction because that way we are going to combine and we are going to give lesser number of molecules and hence we'll have more space, right? So we'll negate the effect of the pressure. So forward reaction will be preferred. Simple. If you decrease the pressure, that means volume, you tend to occupy more volume. You will have, say, more volume, right? As per Boyle's law. So in that case, you would say, boss, let's do the reaction where we can multiply, where we can increase the number of molecules. Backward reaction would be preferred because here you had 2, here you had 3. So, simple thing is, for any reaction, you figure out your delta N. What is delta N? Delta N is the number of gaseous molecules on the product side minus the number of gaseous molecules on the reactant side. For example, in the previous case itself, we had 2 molecules of hydrogen combining with 1 molecule of oxygen to give me 2 molecules of water, all in gaseous state, assume, okay. So delta N here would be 2 minus 3, right? 2 is the total here, 2 plus 1, all are gas, so it's 3. So delta N would be 2 minus 3 minus 1, right? So this would mean that forward reaction is preferred in case of higher pressure and backward reaction is preferred in case of lower pressure. So just figure out that where the number of molecules is less, wherever the number of molecules is less, that would be preferred higher pressure. Forward reaction, higher pressure. Backward reaction, lower pressure. Right? Next, volume. What about volume? What happens to volume? The same thing as pressure. The volume is more, you will prefer to go to the side where more number of gases can be formed, right? You will prefer the forward reaction if the forward reaction side, the number of gases molecule is more, that is the product have more gases molecule, and you will prefer the reverse reaction if it is ulta, okay? So pressure and volume, you can think of it in the same line and you can figure it out, okay? Now let's say one more is addition of inert gases in a gaseous reaction. Okay, so this is very simple. This is for you to think. Let's say the sealed container, you add more of inert gases. Inert gases don't do anything. It just sits there, it occupies the space. So what is happening? Think. It is occupying more space. That means you have less space available for the rest of the molecules, right? Less space means more pressure. More pressure, we have already figured out. More pressure will prefer the reaction side, which has lesser number of molecules. So if the reactant side has lesser number of molecules, backward reaction. If the product side has lesser number of molecules, forward reaction. Simple. Inert gases don't take part in reaction, just sits and occupies space. If it has occupied space, then That means the total space available to the remaining molecule is less. Total space available to remaining molecule is less means reaction will on that side will be preferred where less number of molecules are getting formed. So if it is on the forward product side, less number of molecules are getting formed, forward reaction. If it is on the reactant side that there is less number of gaseous molecules are there, backward reaction. Simple. Catalyst. What happens when you add catalyst? So if you add solid catalyst, for example, what happens? So catalyst don't change the equilibrium of a reaction. It doesn't have an effect on the equilibrium of a reaction. It only changes the speed of the reaction, right? So if in that example, if you remember, 3 by 5 mole of NO2 and SO2 was getting used. So when you add catalyst, that will only happen faster. It is not going to change the amount of SO2 or NO2 that will be used, right? So it doesn't have any effect on the equilibrium. It only speeds up or reduces the rate of reaction. The catalyst will not have effect. So simple. Le-Chatelet principle is simple. It only, any changes that take place during a reaction, the reaction will proceed in such a way so as to negate those changes, right? What are the 5 points we looked at? Addition of reactants and products, addition of reactants, forward reaction preferred, removal of reactant, backward reaction preferred. That means more of the backward reaction will happen. Equilibrium will shift to the left. Addition of product, it will tend to use up those products, so backward reaction would be preferred. Removal of product, it will tend to form those products that have been lost, forward reaction would be preferred. Addition of increase of temperature, endothermic reaction would be preferred, exothermic reaction would not be preferred. Reducing of temperature, endothermic would be not preferred, exothermic would be preferred. Increase of pressure, reaction where the molecule is less is preferred, reaction where number of molecules is more is not preferred. Reducing pressure, ulta, reducing pressure means where more molecules are there that would be preferred, where less molecules are there won't be preferred. And same thing with volume and same thing with inert gases. Okay, so that completes the Le-Chatelet's principle. So that's enough theory to get you started with solving these the questions based on chemical equilibrium. Just try to visualize whatever we have done till now, read through it, and then look at the solved problems, and then you go ahead with solving the numericals, and you will find it easy to solve it. Okay, thank you.